Hey guys, Mr. Brown here, and in this video we are going to talk about mechanical waves. Waves are something you probably already have a general idea about, but in this chapter, this lecture, we're going to define them as something that carries energy from one place to another. We're going to look at characteristics common to all waves. We're going to talk about how we can define them in simple mathematic terms. And then we are going to look at some common everyday waves and their behaviors. So if you'll follow along with me, we'll start learning about all the different types of waves. So we have a definition of waves here on this slide. And we've also got a pretty awesome picture of a cool ocean wave, something that we probably, or some of us, have experience with. And it will help us kind of define what exactly a wave is. So waves of all types are these disturbances that travel across distances carrying energy. So the energy from a wave may come from, for example, in the picture here, the tidal forces, the forces of gravity of the moon pulling on the water. And that gives some energy to the water. But the important things about waves are they do not necessarily carry that matter with them. To our ocean example here, a wave can travel very, very, very far across the ocean, and it transports the energy, but that water that is rising up and then falling down to create the wave doesn't necessarily move with it. The energy just moves through it via the motion of the water up and down. Of course, when it gets closer to the beach, due to friction, some of the water is pushed toward the ocean, but not all of the water that's involved in the wave. Most of the time, the matter carrying a wave doesn't move from one place to another. It may bob back and forth due to the wave motion, but it's not displaced by any amount. After the wave has passed, the matter finds itself in the same position that it was before. There are some waves, most waves, and the waves we are going to talk about in this lecture do require matter to travel through. Some waves, notably electromagnetic waves, do not require matter to travel through. They can travel through empty space. We'll say something briefly about electromagnetic waves on the next slide, but that's all we will talk about them for this lecture. We have an entire module devoted later in the course to electromagnetic waves in particular, so we'll talk more about them later. As I just mentioned, for a brief moment here, we will discuss electromagnetic waves, just mainly due to their difference from the mechanical waves that we will focus on for the rest of the lecture. So electromagnetic waves are these energetic type of waves that do not need matter to travel through. They transmit light and other electromagnetic energy such as X-rays and radio waves. Like I said, we're going to study these later on in a different module. In this module, we focus on mechanical waves, but it's important that we highlight electromagnetic waves so we can tell the difference between the two. Electromagnetic waves, as you'll hear me say later on, they're really important, and it's important that they don't need matter to travel through, because that is how we get our energy from the sun, and that is basically the source of all energy here on planet Earth. It ultimately comes from the sun in the form of electromagnetic waves. So we will give a full study of those, a full complement to the electromagnetic waves later on in the semester. And in this lecture, we're going to focus on our mechanical waves that do require matter to travel through. We'll look at those starting next. So now we see this is what we're going to focus on for the majority of this lecture, these so-called mechanical waves. These are sources of energy or waves of energy that travel through matter. When a wave is traveling through matter, for instance, when a wave is making its way across the ocean or across the pond in some body of water, then the matter that the wave is traveling through is called the medium. So in the case of our ocean waves, water is the medium through which our waves travel. Mediums can include matter of all types. We can see waves in solid, liquid, and gas states of matter. There is no barrier to having waves travel through all three of those different phases. Again, the important characteristic of a wave is that it carries energy through matter without causing the matter to travel. You can see that here in the animation we have of an ocean wave moving across open water, if you will. Now, due to friction forces, we can see that some of the water molecules at the surface will kind of travel along with the wave. But a little bit deeper down, the wave energy is simply being transported by the up and down and circular motion of the water molecules, and they are not displaced very far or even not at all in some of the deeper water. Those water molecules find themselves in the same spot both before and after the wave passed. All that happened was they moved or oscillated in place as the energy of the wave moved through. Some other examples are sound waves and the waves we see on musical instruments such as guitar strings. So we'll talk about the characteristics all of these types of waves share together on the next couple of slides. Before we go into the specific characteristics of waves, we're going to stop a minute and talk about the two major classes of mechanical waves, and those are longitudinal waves and transverse waves. Transverse waves is actually the one that we have a demonstration of here in the animation. Transverse waves transmit energy opposite to the direction of travel of the medium carrying the wave. So the difference between longitudinal and transverse waves is the way in which the matter carrying the wave moves. In a transverse wave, like we see here, the matter itself moves up and down while the energy is actually moving from one end of the guitar string to the other. So the matter is moving up and down this way while the energy is moving back and forward across the string. The matter is moving perpendicular at a 90-degree angle to the direction of travel of the wave as it moves up and down the guitar string. Water waves and the instrument that you see here are great examples of transverse waves. We'll look at examples of longitudinal waves on the next slide and see how they are different from transverse waves. And here on this slide we see the example of the other type of wave we're going to take a look at, and that are the longitudinal waves. Longitudinal waves transmit energy parallel to the displacement of matter, and the best example of a longitudinal wave we can give is that of sound waves. And you can see here in the illustration how sound waves work. When a speaker moves back and forth due to music being played through it, it pushes air molecules back and forth, and those air molecules push the air molecules next to them, and they kind of bounce and vibrate back and forth in the same direction that that wave of energy moves through, as you can see it moving through the air in the speaker in the diagram there. So sound waves are a great example of the so-called longitudinal waves, and we contrast them against the transverse waves. The transverse waves have the movement moving perpendicular to the movement of the matter, where in the longitudinal waves we can see the wave moving along in a parallel format to the matter that is moving. And here on this slide we are starting to take a look at how waves are characterized mathematically. So we're not going to go too deep into this, but we are going to talk about the very broad topic characteristics that all waves share. And a lot of information about a wave can be conveyed with the following four main characteristics, and they are the amplitude, which is often symbolized with a capital letter A, which is the amount of distance the matter carrying the wave is displaced from its starting location. So you can think of that as the letter X here in this diagram. How far does that wave move up? How far do the water molecules that form this wave move up from their so-called rest position here as the wave goes by? That is what we describe as the wave's amplitude. The wave length is the distance from one point on one wave to the same point on the next wave. often measured from crest to crest. Now you can measure anywhere on the wave that you want to. You can measure from crest here to crest here. You could measure from the wave that's at the rest position here to the wave that's at the rest position on the next one. You could measure trough to trough if you wanted to. And all of those should be the same measurements, and we call that measurement the wave length. The next characteristic we have indicated there is the frequency, and frequency is often symbolized with the small lowercase f. And frequency tells us how many waves are passing a given point in a certain second. It's basically telling us how quick that thing is, that wave is vibrating back and forth. It will tell us if I put a point here in my maybe a float or something in the ocean, it will count how many times that float moves up and down every second, and that's what we refer to as the frequency. Finally, we will also describe the wave speed, how fast. We talked last week about the velocity of objects, and we can also talk about the velocity of a wave. How fast is it moving? Is the energy moving through that matter? And we're going to describe that speed in the same units that we use for velocity of objects. Meters per second. How many meters is that wave of energy covering through our matter every second? We'll look at the relationship between the wavelength, frequency, and that wave speed on the next few slides. So here on this slide, we will take a look at how to start manipulating the wave speed equation, which says the wave speed of any wave is equal to its frequency times its wavelength. And so just like we saw with particle speed or object speed, given any two of those three variables, we can always figure out the third one. And so we'll take a look at how to solve some problems involving calculating the wave speed of some waves, the wavelength of some waves, as well as the frequency of some waves. I've given you all of the variables and the units that they're going to appear with in your questions here. So it says the V is equal to the wavelength times the frequency, and V is measured in meters per second. Wavelength, which is symbolized with the small lowercase Greek letter lambda, has the units meters. So wavelengths are always a measure of distance, and we're going to always measure them in meters. And then finally, frequency will often have the units hertz, and hertz just stands for per second. And remember, frequency tells us how many waves pass a point per second. So if we know how many waves pass a point per second, and we know how long those waves are, we can figure out the wave speed. We can also manipulate this formula to figure out what a wavelength is given speed and frequency, and we can manipulate this formula to figure out what a frequency is given speed and wavelength. And those formulas rearranged look like this. The frequency should be equal to the speed of the wave divided by its wavelength, and the wavelength should be equal to the speed of the wave divided by the frequency. So using these three formulas, we should be able to solve for any one of the variables given the other two variables. And we'll see some of those practiced in the next couple of slides. Okay, so here we have the first example question we're going to work with the wave speed equation. It says a sound wave has a frequency of 256 hertz and a wavelength of 1.35 meters. What is the speed of this wave? We learned on the previous slide that the wave speed equation says the speed of a wave represented with V is equal to the wavelength of the wave times its frequency. So we're going to read the problem there and see if we can figure out what the frequency and the wavelength are. We see that is pretty easily spelled out for us in this problem. A frequency of 256 hertz, 256 waves per minute. And we're also told the wavelength Each of these waves is 1.35 meters in length. So the wavelength is 1.35 meters. So to figure out the wave speed, we're going to multiply that frequency by that wavelength. Wave speed equals frequency times wavelength equals 256 hertz times 1.35 meters. And now we simply have to punch that in our calculators. And if we do, we arrive at a number 345.6. And we also learned that the velocity of the wave is measured in meters per second. Since hertz is per second, multiplying meters by the hertz gives us the units, meters per second. So that tells us every second this wave is moving across its matter that it's traveling through at a rate of 345 meters. This is the second example we are going to look at using the wave speed equation. This question reads, an ocean wave travels at 4 meters per second with a wavelength of 2 meters. What is this wave's frequency? So now we need to use one of the rearranged versions of our wave speed formula because we are solving for frequency instead of the wave speed. So if you want to go back and look at the slide where I rearranged the formulas, you would find that the frequency of a wave is equal to the wave speed divided by the wavelength. So if we can just figure out the wave speed and the wavelength from our question, we can answer what the frequency is. And that's pretty easily determined from this question. We see that the wave speed is given to us. It's not expressly said as the wave speed, but we know that wave speeds have units of meters per second. So that's going to be our wave speed here, 4.0 meters per second. And the wavelength, rather, we're solving for frequency, the wavelength is 2.0 meters. And that was an errant mark. That was supposed to be just an equal sign there. So now I've got the variables I need to solve for this formula. All I need to do is plug everything into my rearranged frequency formula. I can see that I put the speed on top, 4.0 meters per second. The wavelength on the bottom, which is 2.0 meters. And I don't even think we need a calculator for this one. The frequency is going to be 2. And the units on frequency is the Hz hertz unit, meaning this wave has a frequency of 2 per second. We have 2 waves cross whatever point we choose every second when this wave rolls by. Here's our third example, and as you may have guessed, this time we are going to solve for wavelength given the frequency and wave speed of an individual wave. So we see that this question says a wave on a string moves at a speed of 20 meters per second and has a frequency of 5 hertz. What is the wavelength of the wave? So we'll go back to our slide where we talked about rearranging the wave speed formula to figure out how to solve for each variable. We see that to solve for wave length, we are going to want to take the wave speed and divide it by the frequency. Straightforward enough if we can just pick those variables from our problem. And I don't think that's going to be much of an issue, as it says the wave speed directly here is 20 meters per second. And the frequency is given to us as 5 hertz. So this wave is moving with a speed of 20 meters per second and it's vibrating back and forth 5 times every second. Let's figure out how much distance there is in between those waves given those variables. The wavelength is equal to that wave speed, 20 meters per second, divided by 5 waves per second, or 5 hertz, meaning the wavelength in this case must be 4 meters. that's a good example of how to solve for the wavelength given the wave speed and the frequency. Here we have another example of using the wave speed equation. This question reads, the speed of sound in air is approximately 343 meters per second. If a sound wave has a frequency of 686 hertz, what is its wavelength? So as we have done so far, we'll kind of revisit that talk of how we rearrange this wave speed formula to give us the variable we want to solve for. This time we're being asked what is the wavelength. So the wavelength is equal to a wave speed divided by the frequency. And in this problem we're told we're dealing with sound, which has a specific speed of 343 meters per second in air. So the wave speed is 343 meters per second, and the frequency is 686 hertz, specifically of these sound waves. So we can see to solve for the wavelength here, we are going to want to take that wave speed, 343 meters per second, divide it by 686 hertz, and the wavelength of these waves, so we can see we got a bigger number on top than a bigger number in the denominator than we do in that numerator. So we're going to expect a number less than 1 here. These wavelengths are going to be shorter than 1 meter is what that number means. Looks to be almost half, in fact. So 343 divided by 686 is exactly half, in fact, so 0.5. These waves, these sound waves, are exactly 0.5 meters in wavelength. Moving on from that, we're going to talk about some of the different characteristics of waves and then take a look at some specific waves, sound waves, and their characteristics and somewhat of our relationship to them as humans. So the rest of the discussion will move away from those math type calculations, and those wave speed calculations will be all we do for the wave section as far as math goes. Now we'll talk about what amplitude means for a wave. So a lot of times the amplitude, how tall or short a wave is, gives us some insight to how much energy that wave is carrying. And I like to liken this discussion to that of tsunamis, which are, as you may know, a large wave in ocean water. So tsunamis happen when earthquakes are triggered either near or under the ocean, and all of that energy is released, all of that movement of the Earth's crust, a large amount of material is moved, and all of that force is transferred to the surrounding water, and that energy carries really very well through that water. Well, when it happens very deep, you can't really see the amplitude of that wave. That's what makes one of something dangerous about tsunamis is out in the open ocean. That wave is moving through very deep water, and so the amplitude of the wave is not very apparent in the deep water. As it moves closer to land, all of that energy needs somewhere to go, so the amplitude of the wave drastically increases as the water gets shallower, and that large wall of water is what crashes in, bringing all of that energy in. That's what makes tsunamis so dangerous. They're oftentimes undetectable until they are close to land, and at that point they're too fast to run from. So that is a big danger with tsunamis, and it kind of tells the story of how the amplitude of a wave really carries the energy of a wave. And as I said a second ago, for the rest of this discussion, we'll take a look at sound waves in particular, because they're such a big part of everyday life. They are perhaps the most common waves to us. We interact with them, we hear them, we feel them on almost a constant basis. So what we call sound is the perturbation of wave energy through the air molecules. It moves from different sources, things that crash, things that hit things that move back and forth, push air molecules, and that energy travels to receivers, if you will, that we have built in, we call ears. And we have an eardrum that vibrates when those waves reach us back and forth, and our brain interprets those vibrations as the sound that we hear. Over the next couple of slides, we'll take a look at how the different characteristics of these waves, the wavelengths and their amplitudes, correlate to what we hear and what our brains interpret as sound. So if you'll follow along with me, we'll finish this up with a discussion about sound energy. And here on this slide, we take a look at the different characteristics of sound, how frequency relates to the perceived pitch of sound in our brains. We can see that low frequency sounds are interpreted as low pitch or bass sounds. They are these types of waves here with these very long wavelengths. So there's a big distance in between the so-called compression and rarefaction. Those are the squeezed together parts and the pulled apart parts of the longitudinal wave. And in higher frequency sounds, those compressions are much closer together, relating to a shorter wavelength. The diagram here on this slide is a really good demonstration that shows when wave speed is constant. So in air, all sound waves move at the same speed. The compression parts all travel along from one spot to another at the same velocity. And when that is the case, we see that wavelength and frequency share what we call an inverse relationship, meaning when wavelength is large, we have a slow or low frequency. When wavelength is short, we have a higher, faster frequency. And if you know much about music, you may already know we actually have a frequency set for all of the different notes in musical application. And here's a diagram of a piano showing the frequency of some certain keys on a piano and the corresponding musical note. You may notice one thing you may take a look at there if you're interested in sort of this stuff. Every time you move an octave up, like say from the key C2 up to the key C3, all that happened was the frequency doubled. So it's the same note, just one extra times 2 higher frequency, and that's how we move up, as they say, octaves in musical recordings. Here we're going to talk about where sound gets its volume. Sound volume is related to the amplitude of the pressure in sound waves. So what that means is sound volume is related to the difference in how tightly squeezed together the air molecules are at the compressions and the rarefactions of the sound wave. If the parts where the compressions are happening are very squeezed together, and the parts where the spreading apart happens, the air molecules are able to get very, very, very far apart, that will be a louder sound than if there is not much very differential between the two. If there's only a small amount of squeezing in the compression stage and then a small amount of release in the rarefaction stage, that relates to a low amplitude. That would actually shorten the diagram showing the sinusoidal version of the wave here. So we would shorten that to kind of relate that pressure change in those waves. This is what determines how loud or soft a sound is. This is related to why you see different speaker sizes for different frequencies of sound. To get a larger pressure differential, to have a lot of air squeezed together and then a lot of it spread back apart at low wavelengths, to get that to happen slowly, you need to move a lot more air than if you need to happen for that to happen really quick. And if you're needing to move a lot of air, that's why we see the low frequency sounds have larger speakers, while higher frequency sounds can get smaller and smaller. They don't need to move as much air to create those pressure differentials at high frequency. Here we take a look at the speed of sound through some different materials, including air, but also other than air. What you'll see if you look at this chart is that the speed at which sound waves travel is highly dependent on the material it is traveling through. So if you look the chart over, you may notice that For solid materials, sound will travel much faster through solid materials than through the air, like we are kind of generally used to. In air, sound only travels at a rate of 340 meters per second. You can often see the kind of effects of that if you think about watching a fireworks display. You can see a bright flash of light, and it takes sometimes quite a few seconds before the sound of that explosion reaches you. But if there were something like steel separating between you and the firework, it would probably happen much quicker, because in steel, sound travels at a rate of 5,960 meters per second, which is almost 20 times greater than it is in air. So it would happen much quicker through solids. It's in between each category. It is also dependent on the density of those materials. So sound typically travels fastest through solids, but within that category, the more dense materials seem to slow it down a little bit, and the less dense materials, for instance, aluminum, has a really, really quick speed of sound of 6,420 meters per second. So that's just a little look at how sound differs as it travels through different materials, and we can see that it's much faster in solids and liquids than we experience in our normal atmosphere. You can see it's about 5 times faster in water. So if we could maybe perform an experiment where we go under water and talk to each other and see if we can make it faster than up on the surface, to kind of visualize that difference in the speed of sound in different materials. That may be the closest we could come to really designing an experiment for that. And since we've had this discussion of, kind of what frequency relates to a sound wave, now we can talk about our sound perception and what that means. Humans typically hear vibrations from approximately 20 to 20,000 hertz. So anything that will shake with a frequency of 20 shakes per second, or 20,000, anywhere in that range, 20,000 shakes per second. Our eardrums will pick up that vibration, and our brain will interpret it as some kind of sound signal. Now, lots of different variations in that sound will add to its characteristics and what it actually sounds like. But we can interpret any kind of vibration generally between those two, between that range. It definitely falls as we get older, and once you cross into adulthood, you typically lose at least 3,000 or 4,000 of that. Most adults can only hear up to about 16,000 hertz. Sounds above that, sounds above 20,000 hertz, are what we refer to as ultrasound, probably a term you've heard in the past before for different reasons, if for nothing else than for the medical applications, which we'll actually discuss here upcoming in just a moment. Just for some fun information, dogs, we all know, can hear much higher ranges than humans can. In fact, they can hear sounds up to about 45,000 hertz. And so your classic dog whistle there generally generates whistling noises in the ranges of 30 to 40,000 hertz. And that's why humans can blow on them, never hear them, but your furry friend can. Bats and a lot of sea animals, including whales and dolphins, use echolocation for either finding friends or prey in different circumstances. And those organisms can both, in some cases, emit and then perceive pitches, vibrations as high as 110,000 hertz, so 110,000 vibrations per second. So that's some pretty high quality hearing they have. At the end here, like I said, to wrap it up, we'll talk about how sound is used in a lot of different technological applications these days. Of course, most of you probably have experienced with, have heard of, have seen at least a picture of an ultrasound instrument that can use sound to image the inside of different things, including our bodies. So ultrasound instruments operate at frequencies of 2 to 20 megahertz. So that's actually 2 to 20 million vibrations per second. So if you've ever seen somebody get an ultrasound when they put that little paddle on you and starting to move it around, the end of that paddle is creating just microscopic, tiny little vibrations that you can't even really feel, but they're there, and they're vibrating at, usually the medical ones vibrate at something like 5 million vibrations per second. And those vibrations move through your tissues, and then they kind of echo, just like any sound does. When you go in a large room and yell, and it bounces off the wall and comes back to you, these sound waves do the same thing. And the little paddle there also receives them and interprets those echoes and builds the images using some computer processing that you see there. These instruments are not just used for viewing babies or viewing organs, viewing inside the body. They are also have been implemented in a lot of industrial applications where we use ultrasound to make these images and review things like the susceptibility or the how well some welding has held up on important applications, such as how well the welds have held up on an aircraft over time, per se. They use ultrasound to also look at things like this in the industry. So that is the presentation for the mechanical waves, including a good discussion of sound. I hope you found some of these topics interesting. As always, if you have any questions or would like to have any more information or discussion about this, please feel free to email me, brownb@sandhills.edu.